Day 354 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again. Another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 95, unique binary search trees 2. The difficulty level is medium, but don't worry because we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, and subscribe. And if you need any new Apple AirPods, go in and check out that link in the description so you can get you some. Now let's see what the question says. Given the integer n, return all the structurally unique BST's binary search trees, which has exactly n nodes of unique values 1 to n. Return the answer in any order, y'all. So it sounds simple enough. They're going to give us an input n, and we want to find all of the unique ways that we can create a BST or binary search tree, meaning there should be each way that we create should be different, right? So let's go ahead and take a look at these examples just to make sure that we're doing this problem correctly, right? So in example 1, we have n equals 3. So that means each binary search tree should have up to 3 nodes, right? Because n equals 3. And we want to determine how many different binary search trees we can create that have up to 3 nodes. Now, it's important to remember that we're dealing with binary search trees, so there's a certain structure that has to be used when we're creating these trees. With the binary search tree, the left side has to be smaller than the root or the current node, and the right side has to be larger than the root or the current node. As you can see here, the left side, the left side, when we have the root node of 2, the left side is 1 because that's smaller than 2, and the right side is 3 because that's greater than 3. So we have to follow those same principles for each node that we create, where as you see in this example right here, we have 1, the right side is greater than 3, but when we come to 3, we have to, the left side of 3 is less than 3. Boom, right? So we have to find all the different combinations of ways that we can create these nodes. So once again, with example 1, we have the input equals 3. The output, we have to return all of the binary search trees. We have to create and return all of the binary search trees. We're not just returning the count. We have to actually return the binary search tree. Now, these binary search trees are not in the same order as the examples, right? So like this binary search tree right here corresponds to this binary search tree right here. As you can see, we start with 1, then we go to the left is null, then we go to 2. Boom, now we're at 2, we come to 2, the left of 2 is null, then we go to 3. Boom. Then we have this binary search tree right here. This represents this binary search tree over here, right? We have 1, we go to the left of 1 is null, we go to the right of 1 is 3. Then we go to the left of 3 is 2, and then we can stop right there because that's the end of the binary search tree. Then this binary search tree right here represents this binary search tree, right? We have 2, the root or the head is 2, we come to the left is 1, come to the right is 3. Now you might be wondering, as you can see, we have 2 binary search trees that start with 1, and we have 2 binary search trees that start with 3, but we only have 1 binary search tree that starts with 2. Now, that is because we cannot create a binary search tree that starts with 2 that satisfies the requirements that are needed, right? So if we did a 2 and we put the 3 on this side, then that wouldn't be a correct binary search tree because the larger element has to go to the right. So we can't put a 3 over here. The 3 has to be on the right side. Boom, and so on with this. We have this binary search tree, 3, 1, null. That represents this binary search tree right here. We have 3, then we go 1 on the left side, we have null on the right side. Then we come to this 1, we have null on the left side, then we have 2, and then this binary search tree right here represents this binary search tree because we have 3 right here. Then we come 2 on the left, it's a null on the right, then from the 2 we come to 1. So these are all of the structurally unique ways that we can binary search trees that we can create of up to n nodes where n equals 3, and that's what we're trying to do. We're just trying to create all of the unique binary search trees that we can with n, with the given n, whatever that may be. So let's go and take a look at example 2. Example 2 is a little bit simpler because n equals 1, so there's only one way we could do it because there's only one node, right? So that one node, 1 is the loneliest number that you ever knew. See, so that's why the output is just 1. So now that we understand the question, y'all, let's get into the fun part, the actual solution. We are going to use some recursion to build these binary search trees for us. So I hope you're excited about that. Now let's get started. Now, excuse me, y'all. The first thing that we need to do, right, as you can see, I already came outside the main function, because the first thing we need to do is we need to create a helper function that's going to generate all of the binary search trees for us within our specific range. So for that, we're going to just create a private func. So we'll say private func generate, we call it generate trees. Open up the parentheses, we're going to say start colon int comma end colon, and that's going to be an integer as well, and it is going to return, open up the square bracket, an array of tree nodes, put a tree node, no s at end, put a question mark, then we're going to open up the brackets. Now we're going to declare a variable called answer. So we say var answer colon. Let's open up the brackets. We'll put a tree node again. Tree node question mark. And we are going to initialize it with a blank array like that. Boom. Now we need to handle our base case. If the range is invalid, then we can return an array with a single nil or just an empty tree, right? So for that, we can say if start is greater than end, we're going to open up the bracket and we're going to say answer dot append, open up the parentheses, just pass in nil, and we can return the answer right away. Boom. Now we need to iterate through all of the values in the range as possible roots. Boom, because remember, we're going to need, as you can see, each value from 1 to 3, we have 1, 2, 3. Each value can be a possible root from 1 to n, right? When n equals 3, each one of these values, 1, 2, and 3, can be a possible root. So that's what we're going to try to do now. So we're going to say, I'll come over here. We're going to say for root and start dot 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 end. So from start to end, we need to recursively generate all the left subtrees with values less than the current root, and we need to recursively generate all right subtrees with values greater than the current root. So first we're going to do the left. We're going to say let left trees equal generate trees, open up the parentheses, we're going to say start colon, then we're going to pass in start, boom, then we'll say comma end colon, we're going to say root minus 1, boom. Now we need to do the right subtree, so we're going to say let right trees equal generate trees, open up the parentheses, then we're going to say start colon, that's going to be root plus 1 comma, and then we're going to say end colon, that's going to be an end, then we're just going to pass in end. Now we need to combine each pair of the left and right subtrees with the current root. So we're going to come underneath these let, and we're going to say for left root and left trees. We're going to open up the brackets. Then we're going to say for right root and right trees. Then we're going to open up the brackets. Now we need to create the current node. So we're going to say let root node equal tree node. Open up the parentheses. We're going to pass in root. Then we're going to attach the left and right subtrees. So we're going to say root node dot left equals left root. Then we're going to say root node dot right equals right root. Boom. Now we need to add the constructed tree to the result. So we're going to say answer dot append, open up the parentheses, root node. Not done yet because we still need to return all of the unique binary search trees that we formed so far and up to the given range. So for that, we're going to come right here and we're going to just say return answer. But don't forget, y'all, we're not done yet because we still need to call this helper function in the main function. So to do that, we could just say return generate trees, open up the parentheses, start, we're going to start, colon, that's going to be 1, we're going to say comma, and end, colon, is going to be n. Now that should be all she wrote. Let's go ahead and give it a run, y'all. See if it runs like it's supposed to. Let's see. Oh, cannot find right trees and scope. Where we at? Oh, sorry, y'all. This should be trees, not tress. Let's run it again. Let's see, y'all. Let's see. And it's accepted. So let's go ahead and submit it. Make sure it's still accepted after we submit it. Ooh, look at that, y'all. 0 milliseconds beats 100% of users with Swift. That's what I'm talking about. That's what I like to see. And you know what else I like to see? I like to see y'all here tomorrow for another day, another LeetCode problem. So make sure you get one more look at the code. That's the top. Oh, excuse me. That's the top. That's the top because we got the helper function. And boom, this is the bottom. And with that being said, y'all, I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.